All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you are all doing well today. I hope you're all doing okay. I hope you are all keeping warm. It is freaking cold again, but it's just for today. That's what I'm going to tell myself. It's just for today, and then it will be warm again, and it will be springtime, and we can just get on with the summer. I hope that you're doing all right today. Today, what I want you to be able to do by the end of the lecture is I want you to continue to be able to describe how an operating system communicates with hardware devices. So time permitting in today's class, we're going to spend a little bit of time looking at a physical hard drive. I've brought a drive with me today, and we'll spend a tiny bit of time thinking about what the physical structure of this thing is, and then think a little bit about how an operating system or just generally how software might communicate with the device that looks something like this. I want you to be able to continue to be able to explain how an operating system provides abstraction around hardware devices. So last class, we looked at this idea that at least on Linux and Unix, everything with giant air quotes is a file. Everything is a file. And that means that the interface for what we're looking at here is we can read a file and we can write a file and do other stuff. But importantly, the interface is composed of these two operations, reading and writing. Anything that can read can work with a file. Anything that can write can work with a file. And thus, if everything, including hardware devices, is a file, anything can work with a hardware device, which is a pretty powerful thing to be able to see. I want to, as part of this, correct the mistake that I made last time trying to get my, my video device to show up on the system. And then what I want to do is spend a little bit of time taking a look at what it means to do things like write to devices, where it doesn't really make a lot of sense to write to that device. Then what I'm going to do is really quickly take a look at an example of a driver in the Linux kernel. I don't really want to dwell on this from the perspective of I care for you to know much about the Linux kernel. I just want you to see that there's some C code in here that satisfies this interface. And I also want to point at and gesture wildly at a Microsoft article that describes how to build a Windows driver. And then that's the end of the conversation about that. It exists. There's documentation for you to do something like this if you want, but we're not going to talk much more about that in this class. After that, we're going to take a look at a physical hard drive. And like I said, this is kind of a time-permitting thing. I brought an actual drive with me today, and I want us to take a look at the different parts of a drive. So being able to identify and name different parts of a drive. And I want to be able to think about things like, if we have this physical structure of a drive, how do we actually service requests for I/O? So given some request for I/O, given some request for sectors on this device, how do we service the request for that physically? What happens with the drive as it's going through this thing? Before we get to any of that, it's Friday today. It is Friday today. So let's take a look at the course schedule and see where we are going next week. So I posted up on the course content page an updated version of the course schedule for week 11. We are very rapidly approaching the end of this course. We're very rapidly approaching the end of the term. You are very rapidly approaching the end of all of your courses for this term, which is great. As I mentioned at the beginning of this week and at the end of last week, we are beginning to step squarely on the toes of Comp.org. We are very squarely beginning to step on the toes of Comp 2280. If you are a friend in engineering, I'm sorry I don't know what the course numbers are for those, but they're computer organization courses. This is where computer science students are starting to think about hardware and how hardware supports operations that an operating system or software might need to be able to do. We're going to be looking at hardware from the perspective of an operating system. And next week, we're going to spend time thinking about this idea of virtual memory. One of the parts of the systems that we have in front of us is that we have this idea of an address space where our processes are having separate address spaces, and we've got threads that share an address space. Well, one thing we haven't thought too much about is how do all of these processes on my system have their own independent address space if I only have 16 gigabytes of memory? How can a process have an address space that's terabytes in size, but I only have 16 gigabytes of physical memory? How does that work? How does that work? Yeah, how does that work? We're going to be thinking about virtual memory, and we're going to have to dwell a little bit in hardware here. We're going to have to dwell a little bit in hardware in terms of how does the hardware support what we need to do? Once we've got an idea of how does the hardware support what we need to do, then we can start to think about what kinds of things do we, an operating system, need to keep in places like our process control block for our structures to represent these different virtual address spaces. And then what does the hardware need to do for us to be able to support accessing memory in these virtual address spaces when they don't necessarily align directly with the physical addresses and the physical memory that we've got here. So what I'm looking for you to be able to do by the end of next week is I want you to be able to explain how a process is an entire address space. And again, this is huge. This is like 48 to 64 bits of space. This is a lot of space that a process can address. How can we have something that's way bigger than physical memory fitting into physical memory? And then how can we have many of those things fitting into physical memory? I want you to describe a little bit about how the operating system works with the underlying hardware to manage that. So to manage paging, we'll get to paging after we introduce the idea of virtual memory, but to be able to explain how the OS works with that, and then begin to compare and contrast some methods for address translation. So this is going to be ongoing, both of these last two topics here, as we get into the idea of paging and then segmentation and then paging. So these are two mechanisms where we're actually supporting virtual memory and virtual address spaces. The two chapters for this week are actually pretty short. They're only like about 10 pages each, and there's a lot of asides in them. So there's not a great deal of content here. We're just going to be beginning to think about address spaces. And I'm really excited about these units. I am personally really excited about these units, specifically the segmentation chapters and segmentation section, because we will finally understand what segmentation fault means. We will finally understand it from when it actually happens to the word segmentation fault being printed on your terminal. We will know the full path, and I love that. I really, really love that, because at least in Comp 2160, when you see segmentation fault, all we can really do is just lower our head and start trying to figure out why it's happening. I mean, you keep doing that here, but you'll understand what's happening underneath. So yeah, I'm really looking forward to that as we get to that in a couple of weeks. The other thing I want to do before we get into talking about our hardware stuff is to talk a brief bit about Assignment 3 and to give you a brief opportunity to ask some questions about Assignment 3 if you have any questions yet. The very first thing I want to talk about with Assignment 3 is that I have published a new sample program for working with the code that you're writing. And so I want to take a look at it, and I want to run it for you so you can see approximately what it should look like when your implementation is set. So the new sample program that I've added is up in the repository here, and it's called nqprefiner.c. So this is the new sample program that you can work with. I'm going to open this up, and I just want to quickly confirm that's big enough for everybody to see. Yeah, okay, awesome. I'm going to go down to the bottom here first. I'm going to go to the main function. In the main function, what we're doing here is I'm creating an interface. I'm creating an application with an interface. I'm creating an application with an interface, and the interface part itself, the thing that's doing the display, it's a thread. It's a thread, and then all of the work are separate threads. And I want to have these things be threaded so that all of these different parts can make progress, and so that the display can be updated as these other things are making progress through the system. So I have a display thread here that I'm creating, and I have a bunch of worker threads that I'm going to create. So in the case that I have set up here, I'm making 40 worker threads. So there's a bunch of threads that are getting created to do some work, and they're going to do their work. They're going to be initialized here in this loop. This is an example that must use the round robin policy. You can't use FIFO with this example. It has to be round robin. Otherwise, it will work, but it will just appear to immediately finish as opposed to actually doing anything useful. So we have to use the round robin policy. We start our scheduler, and then we wait for all of the threads to join in the main function. So after all the work is done, the main function is going to print out this all done message. The display function that's getting worked on is this one here. So it's called Grapher. It calls this function display progress while all the work is not done. Work is done here by different threads of execution adding to their work. This is a counting thing. They're counting up to whatever the max progress is for this system. So they're going to count up to 20 or 40 or something. And they're going to do this by calling a random function to say, like, to give some variability in the output of what they're doing. The display progress function will print out some stuff. This line here clears the screen, so it will cause the terminal to clear itself so that when we print more stuff, it's going to just appear where the old stuff was. And so this is kind of animating the display output. So we clear the screen, and then we print out a bunch of progress bars, and then we clear the screen, and we print out a bunch of progress bars, and we clear the screen, and we print out a bunch of progress bars. The actual work that we're doing here, like I said, every one of these workers gets their own progress bar to work on. Every worker is going to increase it by some random amount of data that they're processing. And then finally, if they've exceeded the maximum amount of the maximum amount of data, so here and here, they're going to set it to the maximum amount of data, and then they're going to exit. So they're going to tell our system that they're all done, they're finished with the work that they are doing. The all full function here is really just for our display to go through and see if anybody is still working. So we want to make sure that it doesn't exit until all of the threads are finished working. So it will keep spinning around until this is done. This program, when it's running, looks a little bit like this. It looks a little bit like that. I'll zoom out so that we can actually see all 40 workers here. But it's going to show progress. And so each of these different threads, there's 40 different threads that we've started up. Each of them are kind of making their own little bit of progress as time goes on. They're all eventually changing their state to finished. They're all eventually calling NQP exit. And then eventually the main thread of execution, our main function, regains control and is able to print out this all done message. This example should work with both the round robin and the multi-level feedback queue when you have it implemented. However, the multi-level feedback queue will look exactly the same as round robin in this case, because all the threads are doing exactly the same thing. They all take exactly the same amount of time and then yield. And then because they're all taking exactly the same amount of time, they're all going to be in the top priority queue doing round robin, and then they will all move to the next level at the same time and then run in round robin. And then they will all move to the bottom level at the same time and run in round robin. So it's going to look exactly the same as round robin in terms of that. But it should work. It should work. I'm really pleased. I'm pleased with myself. I'm really pleased with myself that I got emoji to show up in my terminal here to show that these workers are done. I'm really pleased with myself that I got that to work, but I also just like the way that this kind of displays. I like the idea that this is showing, you know, every different thread is making some kind of a progress here as the system is working. This will work with FIFO, but the appearance that you're going to see is that either there's no display and then suddenly everyone's done, or you will see no display and suddenly everyone's done and then it's finished. You won't see this individual progress being made because we're not preempting our threads. Yeah.
I think you should add dots so that all the progress that isn't done is dots, and it changes to the pipe sign.
Progress. Whoops. Minus progress I. J++. I don't think I'm going to update this in the repository, but okay. There you go. Yeah, okay. So yeah, I'm not going to update this in the repository. If you want to add that little Easter egg, you go right ahead. But again, what I like about this is that we have this display thread. The display thread displays stuff and then allows all the other threads to do some work. And then the display thread comes back and displays the current progress and then allows all the other threads to do some work. And it kind of keeps cycling like this. And I'm really happy with that. I really like the way that this looks. There will be at least one more additional sample program that I'm going to post to this repository. The final sample program that I'm going to post to this repository will have threads that do different things. So they're going to do different things and they're going to have different characteristics. There will be an interactive thread that yields often, and there will be a thread that's doing hard work that goes to sleep for quite a while and then yields to try and force us into a situation where we have threads that are going to be causing themselves to move around in these queues as opposed to everything being moved all at the same time in the queue structure that we've got. And with that, I want to know if you have any questions about the assignment. I'll hold this up here for about 5 seconds, and then I'm going to pop over to the Mentimeter. I also am happy to answer verbal questions if anybody has any questions that they want to ask by sticking their hand up. I'm going to pop over to the Mentimeter now. I do have another question that I want to ask you before we get to you asking me questions. This is something that I see when I drive here. Almost every time I drive here, I see this. Zooming in is not doing anything. Just hold for a second here. I see this almost every time I drive here. And it took me a really long time to realize that it was Waldo. It took me a really long time to realize it was Waldo. If you don't know who Waldo is, it's a kid's book, and it's like really crazy complicated pictures with all sorts of crazy complicated things going on. And the goal is to find Waldo in these crazy, crazy complicated pictures. And these books in English are called Where's Waldo? And that's the game, is to find this. And so to find Waldo out in the wild like this is kind of funny. So my question for you is, where is Waldo? And I'll show you. I'll show you after you guess here. I'll give you about 30 more seconds to answer, and then I will show you where Waldo is. I'm actually moderately impressed that you're picking the quadrant of the city that would be where I would be commuting. Maybe a little weirded out, but moderately impressed. I think that means, oh no, that just means that 2 people have picked the same spot. Okay, I'll give you like 5 more seconds. Okay, so that's impossible. That is 100% impossible to see. So let me show you where Waldo is. Waldo is right there on that building. And if you are going southbound here and you look out to the side, Google Maps has been here since Waldo has shown up. That's where Waldo is. What's going on here? No, I don't want to go there. I want to be here. Waldo is right there. That's Waldo right there. Yeah. So if you're driving south on Route 90 in this area of the city, you can look out your left side window, your driver's side window, and you can see Waldo. All right. So the point of this was to actually allow you to ask questions about the assignment and not just for me to tell you about where Waldo is. So like I said, if you have any verbal questions, I'm happy to answer them. I can begin by priming you with some questions as you're typing that I have had from students either on the course forum or just in person. Okay, I got a question here right away. So excellent. How big should the stack be? The size of the stack that I did, there's a variable that you can get from signal.h called SIG-STK-SZ. I will type that out in just a second. It stands for sig stack size or signal stack size that tells us how big a signal handler stack should be. That's the value that I used for this. I'm going to type that out really quickly. Oh no, I want to keep presenting this. Sorry. I'm really sorry if I kicked you out. The one that I'm looking for here is SIG-STK-SZ. SIG-STK-SZ. And this comes from the signal.h header file. I can post a link to this up on the course webpage alongside the assignment, or I can update the assignment document to describe that. I had also, prior to using this, just picked a random number. I picked 0x1000 as the size of my stack, and that seemed to be big enough. Like, it never actually crashed, but this is what I've seen in other places for examples of doing something like what we're doing. Make context requires me to specify the number of arguments being passed. However, when we create a thread using NQP thread create, there's no argc, so we can't know how many arguments are being passed. We do actually know how many arguments are being passed to this, and it's always one. It's exactly one. There's only one thing that can be passed to NQP thread create as an argument, which is a pointer to void. And it's the same sort of structure as what was going on with pthread create. There was one thing that we could pass to it, and it was of type void pointer. Within the function itself, so I'm going to pop back to the code that I was just showing you here. Within the code itself, within these examples, the functions that I'm passing here always take exactly one argument. The arguments that I'm passing here are pointers to numbers that are on the stack for the main function. And then within the actual function itself, so that's here, this is refined macro data, we take as input one void pointer, and it's our responsibility to cast that void pointer to something. When we were doing this with the thread pool stuff, I showed an example of using pthreads, and then we're casting that structure type. If we're passing a structure to one of these thread pools, we have to cast it to the specific type. So in terms of doing the make context function, the arguments that you pass here, can be a hard-coded value of 1. This can be a hard-coded value of 1, and then what you pass in var args here is going to be the void pointer that was passed to your NQP thread create function. Is 1 megabyte too big for a stack? It might be. I guess it depends on where you're allocating that stack. If you're allocating the stack as a stack allocated variable in the main function, it might be too big, because if you have a 40 megabyte stack, things might start to go crazy if you do something like having 40 threads starting up and all of them have each 1 megabyte stack. I guess my advice here would be to use that sig stack size variable or pick something much smaller like 0x1000 or 0x2000 for that. Will the function that was invoked in NQP thread create always call NQP yield and NQP exit? So this is a good question. This was something that was also asked to me verbally. The functions that are invoked in NQP thread create must call NQP exit. They have to. They absolutely have to. And so you can safely assume that any thread that gets run or any function that gets run by this or passed to your code will always call exit. It will call exit as the very last thing that it does, unless it's intentionally designed to run forever. They won't necessarily call NQP yield. It's possible for a thread of execution to do what it needs to do and then exit. And then at that point, exiting has the same behavior as yield, with the addition of we're removing that thread from the system and scheduling another task, if there are other tasks to schedule. So it's possible for this function to not call NQP yield and only call NQP exit, but it probably is going to call NQP yield a bunch of times. You do not have to deal with the case where it doesn't call NQP exit, and you don't have to deal with the case where it doesn't call NQP yield ever really, because we don't have preemption. We can't preempt these tasks. The only way to take control back would be for you to do preemption, and we're not doing that. So you can safely assume, as I said, that it will always at least call NQP exit as it's leaving. It may call NQP yield while it's working. Should lock be used in the implementation of threads, or is it the caller's responsibility to use locks? It's the caller's responsibility to use locks. The one place where it kind of feels like a reasonable choice to use a lock is in the join function. That's the one place where it might be reasonable to think about using a lock, but I would advise you not to use anything that looks like a lock in the yield, I'm sorry, let me restate that just to make sure that I've used the same word in both places. The one place where it might be reasonable to use a lock, or might feel like it's reasonable to use something that looks like a lock, is in the join function. That's what I'm trying to say, in the join function. The semantics of the join function with pthreads is wait until that thread has finished. Wait until it's finished. The problem with waiting for us, for anything in this code, is that as soon as we wait for something to happen, we will never stop waiting. We just get stuck. And so if you did something like put a spin lock type structure into NQP thread join, that thread will just spin there forever if that thread is currently running, and it will never leave because it won't give control back to the scheduler to be able to take that other thread and put it back on the queue again. So the join function itself should yield. It shouldn't actually, if that thread is still working, it should yield to allow that thread to start running again. But locks themselves will not be used in the implementation of threads. Locks may be used in additional sample programs that come out, but they're not going to be used in the implementation of threads. MLFQ requires a priority boost after a certain period of time. So yeah, we're going to have to boost after a certain period of time, but the only way that we are able to take time measurements is when we have control, when we're able to actually start doing MLFQ. So my advice to you here is we didn't learn how to do a timer interrupt, and we kind of can't in this situation because we don't have any preemption. We don't have any way to like stop execution when something's happening. For the priority boosting part of MLFQ, the job here is pretty much when you start scheduling, take a look at the current time, to capture the current time when the scheduling process is starting, And then when you start to do MLFQ again, take the current time. And if the difference between the current time and the time when the boost period started exceeds what S is, then do the boost. But you have to do that in the context of where you're actually doing the scheduling. So mark down the time when you start, mark down the next time when you start to do scheduling, take the difference and then see if that's bigger than S. And if it's bigger than S, then boost everyone's priority. If it is bigger than S and you're boosting everyone's priority, reset that boost time to whatever the time is right now, and then proceed basically. So that's really the only way to accomplish that with the system that we have set up, is to kind of just keep track of how much time has elapsed ourselves. Functionally, this is going to look pretty similar to how you're making decisions about when to down prioritize a thread. So how much time it's spent running on the CPU will look similar to the calculation of how much time has passed in terms of deciding when to boost everyone's priority. I'm confused on how to make my own thread control block. That's a fair question. So minimally, this is going to be a structure. This is going to be a structure that contains an instance of that uContextT. So the thing that you get back from the getContext function, that and a stack, so that you have a stack for that thing. In terms of getting started with doing threading, that's the only things that you need is the uContextT and the stack for it. Getting to FIFO, you also only need uContextT in the stack. Doing round robin, you only need uContextT in the stack. And it's only once you, start getting to MLFQ that you add to things to your thread control block structure. And adding things to your thread control block structure here is going to be like metrics about how long that task has spent running on the CPU, so that you can decide what priority it should be at. That could then also be you embed the priority in that structure as opposed to putting it into different queues, into different physical queues. You just use one queue that has priority, and then you put the priority inside that structure. But it's ultimately just a structure with at least two properties, the uContextT for the thread and the stack for the thread. We'll hold here for like 10 more seconds. All right, cool. Okay, I will try to give some more time for questions at some point next week, and I will try to make sure that that happens at the beginning of class. Oh, there's one more question. Why is so why is MLFQ implemented with one queue? This is completely up to you. It's completely up to you how you want to implement MLFQ here. MLFQ, as described in our textbook, the visual diagram that they show is a list of queues where we have entries in position 0 is like the highest priority queue, position 1 is the next lowest priority queue, position 2, position 3, and I think they have like 7 in the list that they've got. But this is a square shape where we could take the square shape or rectangular shape and just like put them all beside each other and make it into a priority queue. So the highest priority things will be the thing that you take off the end of the FIFO first. The lowest priority things will be the things you take off the end of that queue last. So you can implement MLFQ with one queue. That's what I'm trying to say. You can implement it with one queue, a priority queue, as opposed to having 5 different physically separate queues. It's possible to do it. It's really up to you, whatever works best internally in your mental structure and mental abstraction of what MLFQ is for that. All right, like I said, I'm going to try to make sure that we've got more time for questions about assignment 3 after the weekend, so that you may have had a chance to work on it a little bit more, and then have some more questions about it. And like I said, I'm going to try to make sure that that happens at the beginning of the class so that it doesn't just fall off the end. I am going to keep this tab open so that I remember to put this up somewhere so that you have a reference to that specific variable. And then we will otherwise keep on trucking along. All right, so let's talk about this idea of hardware devices and abstraction again. So as we saw last time, Unix takes that single interface idea too far, in my opinion, in terms of making everything into a file. I really think that that's a powerful idea. Don't get me wrong, I'm not mad at Unix for making everything in a file. I think that's a really powerful idea because now I can do things like run programs on the command line that read a webcam and are able to show the webcam's content even if they don't know how a webcam works. As long as they know what the data is that's coming out of that file, they're able to work with the data that comes from that file. They don't have to know anything about how that stuff works. So I want to start by fixing a mistake that I made last time. And the mistake that I want to fix is when I was taking a look at our dev file system here, there were these video files that represented all of the different webcams that I have attached to my system right now. I actually only have 3 webcams attached to my system right now. I don't know why there are 7 devices. There's 8 devices here, I guess. I don't understand why there's 8 devices. I have 3 webcams attached. I've got one that's the front camera, one that's the back camera, and then I have a USB webcam that's attached to my system. That's 3 devices. That would be 6 files here, because for reasons I also don't understand, the audio is separated as a different video device here. I don't understand why. I don't understand why. I'm just accepting that this is the case, but I still don't know where the additional video files are coming from, because I can only count up to 6 here. I'm going to run this command that left me kind of embarrassed here last time, where I had this magic argument here that was lavfo set input format mjpeg, which we don't need to know about. All we really need to know is that MPV is a program, and we're passing it the name of a file. And the name of the file that we're passing here is devvideo0. And now it works. Okay, yeah, so this, I'm going to stick my finger right in your faces here. That's the webcam that's on the front of my system. As far as MPV is concerned, and I might actually use this later, as far as MPV is concerned, devvideo0 is a file that has video data in it. MPV does not know how to work with webcams. I had to tell it what the format was. That's what this magic argument is here. I had to tell the program how to interpret the data that's coming from the file, but it was just reading a file. It was just reading a file, and the file was the specific device that we had attached to the system. The other thing that we saw last time was, I'm going to go to this input directory, and there are these mice devices. There's mice, and then there's mouse 0 through 4. As I mentioned last time, there's a surprising number of mice attached to my system because of things like the touchpad, the touch screen, and the pen display are all showing up as different mice in my system. But I can do things like, and this time I have to use root to do this. So I can do things like hexdump -c mice. And I have to do this as root in this case because the mice are globally attached to the system, and for any user to be able to read the mouse would be a problem. If you could log into a machine on Aviary and read the mouse, then you would know what that person is doing with their cursor right now. So I don't want to be able to read this file as a regular user. I have to be an administrative user to be able to interact with it. But once I have it open, then I'm able to read the file that is the mouse. I'm going up here, I'm going to the right here, I'm going down, and I'm going to the left here. Hexdump doesn't know how to use a mouse. It does not know how to interact with the mouse, but it does know how to read files. There's nothing meaningful happening with Hexdump. It's just reading the file. And it's blocking right now because there's no data in the file for it to read. But the idea of a program being able to read this file without having to understand how the weird USB connection between my keyboard and my tablet works, without having to understand how touch screens work, and now I'm touching my screen and doing the same thing here. It doesn't have to know how touch screens work. And I also have a pen. It doesn't have to know how pens work. It doesn't have to know how each of these different devices works. It just has to read a file. It has to know what to do with the data, which is why we have to tell MPV, this is the format of the file that you're reading. But we're able to get to pretty powerful states by really just saying, this is a file, and any program that can read a file can do something with that. I'm going to exit this program, and I'm going to pop over here to my web browser. And one thing that I put alongside today's lecture notes is a couple of supplementary links. I'm going to zoom out just a little bit. I'm going to go to week 10, and we're in lecture 28. The one that I want to take a look at right now is this one. This is a file that's called mousedev.c, and you'll note that it's in the drivers folder. This is Linux kernel source code. This is a driver for the Explore PS2 device driver. Explore PS2 is like this ancient Microsoft mouse. Mice are pretty standardized, so one driver generally works for all mice, even though the different devices themselves might be different. There's a lot of stuff in here. There are structures that represent the mouse that will tell us things about, which way it's going. There are locks here, which is actually kind of interesting for me to see. I didn't notice that the first time there's a spin lock here. I'm going to scroll past a lot of this, and I'm going to go actually pretty close to the bottom. And pretty close to the bottom here, the part that I'm really interested in seeing, I think it's on line 749, 773 right here, is this one, static construct file operations. And this is a structure that has a bunch of function pointers to within this file, and it implements things like read. So when we're reading this file, when we're invoking the read system call, not necessarily from this file, but a file that looks like this one, its read function is going to be invoked by the kernel, by the operating system. There's an open, and that also makes sense. We need to be able to open the device because it's a file. I want to be able to open the file that's on the file system. But kind of confusingly to me, there's a write. And that means that there's code that's going to be invoked in this file when I call the write system call on one of those mouse files, or something that looks like one of those mouse files. I'm going to go to my terminal here, and I'm going to change directory back to where I was. I've just zoomed in here, so I'm going to close this terminal, actually. This is a Git repository that I have put up alongside the course material for today's lecture. This has a file in it that's called mousemover.c. I can't claim to have authored this myself. This is adapted from a Stack Overflow post. I've linked to that Stack Overflow post in the README file, so you can find where I got the bulk of the code for this from. This is a piece of code that uses a couple of structures that are provided by our operating system. It takes as input one argument. It will try to open that thing. It will start to set up the structures themselves, and then it will write to that device. It will write to that device. And then it will go to sleep for a little bit. And then it will keep doing that a couple times, and then it will eventually exit. I'm going to quit this. I'm going to make it. And I'm going to take a quick look at my README file. We have to figure out which mouse to look at. And so the way that we're going to look at which mouse to look at is to run this command. grep-c, uppercase C here says context. I want you to print the 6 lines before and the 6 lines after the one that matches this one. Proc is a file system that we've seen before in terms of looking at processes that are running on the system. there's a folder inside of our proc file system called bus. This is all of the devices that are attached to a bus on the system. So this is giving us a list of information about devices attached to buses on the system. There's an input bus. These are input devices. And then this file devices is the list of all files that are input devices on our system. And I want to be able to find out what the name are for each of these things. So I'm going to copy this command. I'm going to zoom out and I'm going to run this command. There's a bunch of different stuff here. So I'm going to page up. There are several different files here, or several different devices that are attached to the system. So you can see that we've got something. I don't know what this one is. This one here literally says the word stylus. This is the pen that's attached to my system. And then we've got the mouse, multiple mice that are attached to the system, a USB keyboard touchpad. What this program takes as input is one of these files, event20. And so I'm going to scroll down just a little bit here, and to run it, we're going to have to pass that device file. So I'm going to say mouse mover dev input, and I'll try in event20 first. And I have to run this as root. For the same reason that I cannot read that file as a regular user, I have to be able to run this as an administrative user. So that's not the right one. I'm going to go up here, event 9, event 7, event 4. There it is. So when I write to this file, it's causing my cursor to move, which to me is like this ultra weird idea that you can cause a mouse cursor to move by writing to a file, but this is the abstraction that we have here. This is what our operating system is providing for us. We can read these things as files and work with their data, assuming that we know what the format of that data is, and we can write to those files assuming we know what the format of the data is to write. We can write to those files and cause events to happen, cause actual changes for these things to happen. I don't know what's going to happen if you write to a webcam. If you write to something that's a speaker or a sound card, you'll get like crazy static coming out of your sound card or speaker because you're just writing potentially random data to a file that hasn't been properly decoded into what the system is expecting it to be. The very last thing I want to show you is the other file that's, the other link that's alongside this supplementary link, which is writing a driver for Windows. Windows is not the same as Unix. Surprise, I know, surprise. It's not the same as Unix, but it also doesn't have the same architectural model that Unix and Linux operating systems do. Devices in Windows are not files. They have handles, they have descriptors. So when we think about file descriptors, this is another word for this commonly is the word handle. They have device handles, so they kind of have the same sort of general vague idea. But drivers here, and I'm going to scroll down. I don't really want to dwell on this very much. C in Windows is also kind of weird looking. There's a lot of uppercase characters to represent different things. This is the end of this conversation. I don't want to talk about Windows. I don't want to talk about Windows drivers. If nothing else, what I want to say is, hey, this exists and you can take a look at it. All right, so on Monday, what we're going to do is we will take a look at a physical hard drive. In terms of the readings, when I'm expecting us to start working on the stuff that we have in readings, then the earliest that we'd be talking about that is probably on Wednesday. We may introduce it on Monday, but we'll probably be more talking about that on Wednesday. So on Monday, we'll take a look at our physical hard drive and start to think about some ideas of I/O scheduling. But at this point, you should be able to describe briefly how an operating system communicates with hardware devices. And you should now be able to explain how an operating system provides an abstraction around hardware devices. So within the context of Unix and Linux, this is the idea that we have to have code that implements an interface, and the interface on Unix and Linux is approximately the file interface. So being able to read and write to files gives us the ability to work with these devices. That's it for today. I hope that you all have an excellent weekend, and I will see you all on Monday. Bye, everyone.